Well, I looked over the recordings from Monday, both for this class and my other one, and it didn't seem to come out too badly. I mean, the picture kind of broke up sometimes in spots, but nothing that kept you from seeing what was going on, so that's kind of encouraging. When I left off, by the way, everybody has all these handouts I gave out on Monday, right? I brought them back because I thought somebody might not have been here. I've gotten this far. The electric field vector. This should be pretty much the last thing in your notes. Okay, Bernie, you weren't here Monday, right? So it's kind of over there. You need one from each pile. Yeah, that's going to be kind of interesting to watch. Anyhow, the idea once again is that you want some way of describing the strength of an electric field. So you've got the field, get this stuff back out again. The field, for example, of this electrically charged rod. Charge up the ball too. So if you want some way of measuring the field, you can put everything backwards in there. You can put this test charge in different places. You can put the charge there and notice how big the force is by how far the little pendulum leans to the side. Or over here at this other point, again, how far does the little charged ball get pushed to the side? The farther it gets pushed, the bigger the force. But the strength of the field at any of those points depends not only on how strong the field is, it also depends on how strongly charged this ball is. The thing that would be a property of the field only is the force per unit charge, okay? If this thing is twice as charged, it will feel twice as much force. It's always the same ratio. So that's how we're going to describe the strength of the field. The T subscript here stands for test charge. And I think I mentioned this right at the end on Monday, but if I did, it doesn't hurt to repeat it. The test charge, by convention, is always thought of as being positive. In other words, the direction of the electric field is the direction the force a positive charge would feel. So that's one difference between electricity and gravity. There's only one kind of mass. No matter what I drop, it goes that way. With electric fields, there are two kinds of charge, positive and negative. One goes that way, the other one goes that way. And you have to pick one or the other of those to be the direction of your field. Well, we'll pick the direction that the positive charge goes. Doing it the other way would have been just as good, but that's not how it was done 200 or 300 years ago when all of this was set up. And so that's the way it's defined. One way it is like gravity, though, you might, well, if you don't remember this, you don't remember much of anything. Physics 131. The way we describe the strength of a gravitational field is with the gravitational acceleration. G is 9.8 near the surface of the Earth. The number gets smaller as your altitude increases, the field gets weaker. G would take on different values on other planets. If I rearrange that, well, of course, weight. the word weight just means the gravitational force. I just rearrange it a little bit. This number that we use to describe a gravitational field is the force per unit mass. This number we use to describe the electric field is the force per unit charge. Charge is to electricity what mass is to gravity. It's the same idea, okay? So this is to an electric field what the gravitational acceleration, or this is to an electric field, but this would be to a gravitational field. Having introduced the idea of this electric field vector, E, you can take Coulomb's law and kind of divide it into two parts, cause and effect, okay? One thing creates an electric field around itself, and then the other thing feels a force because you've placed it in that field. Now, the field of a rod is actually a little more complicated. That's not described well by Coulomb's law. We'll save that for a little later in the course. But if I had two of these things instead, two charged balls, so that Coulomb's law accurately described it. First of all, the field produced by one of the charges. Force per unit charge, and the force is given by Coulomb's law. I don't need the absolute value signs on my test charge because it's always positive. I mean, they don't hurt anything. Put them on there if you want to. The point is that if you're talking about the force per unit charge, one of the Q's gets canceled out of Coulomb's law. So the electric field, a distance r from a point-like charge, is the Coulomb's law constant times q over r squared. Other half of the story is that the other charge, Q2, gets placed in this field. How much force does the charge feel? Well, you just take this and multiply both sides by Q to solve it for F. So again, basically split Coulomb's law into two steps. Step one, a charge Q creates a field whose strength can be calculated from this. Step two, the other charge feels a force that can be calculated from this. And then, of course, there are the inevitable examples. So first of all, number 2. over here. There's a negative 20 microcoulomb charge sitting at the origin. And for some reason, you're interested in what's the electric field at that point up there in the second quadrant. So the electric field is a vector. We have to take its direction into account. But taking things a step at a time, let's start out with how strong the field is. And then after a minute or two, I'll bring the direction into it. So as far as the magnitude, well, like I just got done saying over here, that formula tells you the magnitude of the electric field, a distance r from the charge. The Coulomb's law constant you can look up on your formula sheet. The charge Q is the 20 microcoulombs given in the question. R is the distance from the charge to point P. I have to figure that out with the Pythagorean theorem. So I'm going down here. Here's point P over here. That's R. This is 2 meters. This is 3 meters. And R then. Well, actually, why bother taking the square root? I was about to start writing down R equals the square root of 2 squared plus 3 squared, but it's R squared that I need in there. So R squared equals 2 squared plus 3 squared is 13. And so you multiply and you divide, and well, this is a lot of digits, but we'll round off when we get to the end. For now, 13,831 newtons per coulomb. That is the magnitude of the field at that point. Now, as for the direction of an electric field is the direction of the force on a positive charge. A positive test charge would be attracted to a negative 20 microcoulombs. Okay, in general, field lines point away from positive charges because positive repels positive. Field lines point toward negative charges. So if point P is there, the direction of the electric field is something kind of like that. It points right straight at the origin, down and to the right. Positive charge would be attracted to the origin, so that's the direction of the field. So if sketch it in, I've got the camera pointed over here now. That's point P. There's the E vector. Y component points down. X component points to the right. And we call this angle here theta. Well, that's the same as that angle theta there, but I no longer have the camera pointed toward. This is going to be a bit of a nuisance, but back over here. So I need, I'll write it down in a moment, but I need this hypotenuse, 13,831. I need that number times the cosine of theta to be the x component. I need times the sine of theta to be the y component. And you could look at this triangle and say that theta is the arctangent of 2 divided by 3. And once you've got theta, you could punch up the sine and cosine. And that's perfectly correct. But if you want to save a step, you might notice you don't really need theta itself. All you need is its sine and its cosine. And on the little sketch here, we have all the sides of this triangle, 2, 3, and the square root of 13. You can just pick the sine and cosine off, directly off of that without fooling around with theta. I mean, either way will work, but in general, I try to do less instead of more when I can get away with it. So the electric field is 1331 cosine theta times I minus, okay, so hypotenuse times cosine gives you the adjacent side of the triangle. And from that triangle back over there, whose sides are in meters, this is 3 divided by the square root of 13. Cosine is adjacent divided by hypotenuse. Or go ahead and calculate theta, it doesn't really matter. Hypotenuse times sine. Picking the sides off of this triangle over here, opposite over hypotenuse is 2 meters divided by the square root of 13. And so, put it all together. That's the answer. That's the electric field vector at point P. I suppose it wouldn't hurt to review a thing or two. Notice the distinction between a vector and its magnitude. The magnitude just simply means how big is it, 13,831. The vector includes the direction as well as the magnitude. In terms of the x and y components, is not the only way to express a vector, but it's frequently the most convenient. X component is this, y component is that. The I and the j are what are called unit vectors. Vectors of length 1 that point in one of the coordinate directions. I means a vector of length 1 unit pointing in the x direction. J means a vector of length 1 unit pointing in the y direction. So 11,500 times I would be a vector of length 11,500 pointing in the x direction, so on. Number 2 is a continuation. Having determined the electric field at that point, well, the electric field exists whether there's anything there to feel its effects or not. But if there is a charge of 2 microcoulombs at point P, notice that the electric field here given question number 3 is nothing more than the answer to question number 2. So it's still a continuation of the same problem. You put a 2 microcoulomb charge up there at point P, and what's the force on it? Well, that would be the other half of, well, what it said right there before I erased it a moment ago. You place a charge in an electric field, and F is equal to Q times E. So the charge that you're placing in the field, convert microcoulombs to coulombs, 2 times 10 to the negative 6. The field that you placed it in is I don't feel like writing it all down again. 2 times 10 to the negative 6 times that. And so you distribute the 2 microcoulombs across both terms. Two times 10 to the negative 6 times 1.15 times 10 to the 4 gives you 0.023. That's the x component. In the y direction, 0.0153. As far as the units, newtons per coulomb times coulombs gives you newtons. Force comes out with the unit of force on it. So, cause and effect. One charge creates this field around itself. The other charge is placed in that field, and as a result, it feels this force. Number 4 is kind of a variation on number 3. I thought it would be good to point out what happens if you stick a negative charge in a field. I didn't stick with the same field this time. Just to keep it a little simpler, I just made it one that points horizontally. (7.2 times 10 to the 7th). Pointing in the x direction, there is no y component, so the thing points perfectly horizontally to the right like that. And in that field, you place an electron. And I guess more or less the main point here anyhow is that if, back up in here, F equals QE. If Q is a negative number, the direction of F will be the opposite of the direction of E. So field points to the right, the force on an electron will be to the left. As far as the details, To get the charge on an electron, you go into the reference table I gave you, part of the formula sheet, and that's on one of the, that's maybe about two-thirds of the way through. There's a table that has various useful physical data on it. It's the same table where you would look up the Coulomb's law constant, among other things. One of the things that's there is, it doesn't say charge on the electron, it says the elementary charge, because it's not just the charge on an electron, it's also the charge on a proton and the charge on a muon and the charge on lots of other things. But if you don't happen to have a photographic memory, that's where you can get the 1.6 times 10 to the negative 19th coulombs. Since it's an electron, you have to remember to stick a minus sign on it. And E, the field, is given in the question, 7.2 times 10 to the 7th, just a little more space. And so you multiply those out, and you get negative 1.15, 10 to the negative 11th in the x direction, measured in newtons. Electric field lines. Basically, how to draw a picture of an electric field. It's not like a bowl full of fruit where you can literally draw a picture of what it looks like. Electric fields are invisible, so you need some way of representing the field. And the way that's done is by drawing a whole bunch of arrows pointing in the direction of the field at various points in the region that you're picturing. So, top of the next page. Lines of force show the direction of the force on a positive test charge, which is to say the direction of the field. So I've got I spent half the class moving this thing around. Got three different pictures here. First of all, a positive charge. That could be a proton, or it could be one of these pith balls with it's been given a positive charge. Whatever it is, if you were to put a positive test charge here, it would be pushed that way. Put a positive test charge here, it would be pushed that way, and so on. Anywhere you put a positive charge, it points radially outward away from this pith ball, if that's what it is. Similar picture over here, except the ball has been charged negative instead of positive. A positive test charge would be attracted to a negative ball, so now the field lines point in rather than out. So field lines point away from positive charges, field lines point toward negative charges. A somewhat more complicated charge distribution down here, a pair of equal and opposite charges. For people who like jargon, that's called an electric dipole. The combined effect of the fields from these two different sources will give you field lines, which technically aren't lines at all because they curve, but people call them field lines anyhow. The direction of the field at any given point is tangent to those curves. So, for example, if you put a positive test charge right here, it would be pushed in the direction of this arrow that I drew, along a tangent to the field line. That's the combined effect of being repelled by the one and attracted to the other, which brings us to the superposition principle. But one other thing I should say first is that if you know what you're looking for with these pictures, you can not only see the direction of the field throughout the region that's being shown, but you can also get an idea of its relative strength, because where the field lines are closer together, the field is stronger. Like around a charged sphere like this, the field drops off in proportion to 1 over r squared. So in other words, the farther away you get, the weaker the field is. Now you look at the picture, the farther away you get, the farther apart the field lines are. So the density of field lines shows you the strength of the field. And of course, the direction they point shows you the direction. The superposition principle. What if you don't have just a single pith ball? What if you have some sort of distributed charge? Well, like this dipole, for example, in this picture here. And you want to figure out what's the electric field at that point right there. Or you put a charge there and you want to know the force on it. Well, the superposition principle says what you do. Now let's take it one case at a time. If there's a charge here and you want to know the force on it, you put a proton there. Want to determine the force. First of all, just pretend the one charge doesn't exist. You've got your proton and you've got this pith ball, and you use Coulomb's law and calculate the force from that. And then after you've got that all written down, now you, for a moment, pretend the other one doesn't exist. And you calculate the force on your proton from that one. And once you've got both of those written down, then what the superposition principle says, just add them together. Where remember, add means a vector sum, because these are vectors after all. It's the same thing if it's the electric field vector is just the force per unit charge, so it superposes the same way that forces do. And I should probably run through some examples of that sort of thing. We'll start out with a one-dimensional example, but of course, when we turn the page, things aren't going to stay quite that simple for very long. Back over there. Number 5. Two parts. Part A of the question asks for the total force on charge A, the one on the left. Part B of the question asks for the total charge on B, the one in the middle. Well, I mean, alphabetical order is all well and good, but I sort of personally have a tendency to do the easier thing first. Like when I'm grading papers and I start going through the blue books and I look at this one, it's like, oh, I'll get back to that one. Okay, that one's right, that one's easy. So the easy part here is the total force on the one in the middle. Actually, if you're on top of things, you should be able to see exactly what the answer is right now without getting out your calculator and doing a lot of figuring or anything. The force on B is 0. Oh, smart people, I like that. Yes, because The force, let's see, B is negative, both the others are positive, so B is attracted to both of the others. So the force on B from A is that way, and the force on B from C is the other way, and both of those forces are given by Coulomb's law. Well, in both cases, it's the same amount of charge, the same distance away, so everything in Coulomb's law is exactly the same for both of these forces, so they're exactly the same number of newtons, opposite directions, they balance each other out. A and C have the same charge at the same distance, so the magnitude of force A equals the magnitude of force C, which means so the total is 0. For A, not quite so obvious what the answer is. We actually have to spend a little time figuring that out. Over there on the left, A will be attracted to B because A is positive and B is negative, opposites attract. So the force on A coming from B is something like that. A is repelled by C, they're both positive. So A is going to be pushed away from C. Something like that. And I drew the arrow for C shorter than the arrow for B because I'm expecting that force to be smaller. The charge is twice as far away. And aside from that, it's not as much charge as B is. So either way, it's going to make the thing smaller. So that's kind of a sketch of what the two forces are that we have to add together. To get some exact numbers for how big they are, force B. Coulomb's law. Coulomb's law constant is about 8.99 times 10 to the 9th power. Product of the charges, 2 microcoulombs. 3 microcoulombs. The distance between them is 0.1 of a meter. And as I already mentioned when I was drawing those arrows, force B points to the right because opposite charges attract. A will be attracted to B. So that's the plus I direction. would like to point out where people sometimes go wrong with this kind of thing. People just love to throw numbers at formulas without thinking about them very much. So because this is a negative charge, they carry the minus sign on through, and they get the direction backwards on the force, okay? This is why I say it's the best to consider the magnitude and direction as two separate questions. Figure out a positive number. How many newtons do you have for the force? Once you've got that written down in front of you, then stick a direction on it by asking yourself, you know, is it attracted or is it repelled? Likes, repel, that sort of thing. So absolute value signs, because I'm calculating the magnitude of a vector, which is a positive number. And then stick a direction on that based on the fact that opposite charges would attract each other. Don't let that minus sign turn things around backwards on you. Do a similar thing to get the other force. Charge C is 20 centimeters away from charge A. So 0.2 is what goes in for R. As for a direction, well, like I already explained when I drew the picture up here, because like charges repel, force C points to the left. So minus I. Emphasize once again, you want to get your plus and minus signs based on opposites attract, likes, repel, not based on whether the formula comes out positive or negative, because that would have been positive in this case, but it actually points in the negative direction. So those are the two individual forces. Really, a lot of this is review, okay? Back in Physics 131, I had you do problems where there was some object. Oh, there was that one lab we did where there was the force table with the little ring in the middle and the three scales pulling on it. And you had to find the resultant of those three forces. Okay, this is just the same stuff all over again, except now the three scales are invisible, okay? Because it's an electric field that's pulling on the thing rather than some tangible object that you can touch with your finger. But aside from having last fall, I usually gave you a question where it told you how many newtons each force was, and you were supposed to add them up. The only thing that's new here is you've got a formula that you have to use to figure out how many newtons each force is. Once you've done that, then it's all review from last fall. So add them up. The superposition principle says that the overall force is the sum of force B plus force C. And that comes out 4.49 times I newtons. Now, if you were to flip through the textbook, you'd find that electric forces and gravitational forces are in two entirely different chapters that are like 100 or 150 pages apart or something like that. But always looking for a more efficient way to use my time, I think it's not a bad idea to talk about them in the same unit, because it's the same story all over again. Gravitational forces between stars, electric forces between protons and electrons. Yeah, it's pretty much the same thing. Different kind of field, they act in the same way. So on the next page, if I can figure out where I put, oh, that's the next page right there. Okay. I have entirely too much stuff up here on this table. So we'll make it, having done a one-dimensional example, I'll run through a two-dimensional example where you have both X and Y components. And just for a little variety, this time I made it masses and gravitational forces instead of charges and electric forces, and it all behaves exactly the same way. Of course, nobody would actually care about the gravitational forces between things that are just a few kilograms. What this really would be about is maybe 3 stars in a triple star system, or maybe some planet and 2 moons or something like that. But I didn't feel like writing a bunch of numbers that had 27 or 30 zeros on the end of them. And it just made it easier if it was numbers like 5 and 3 and so on. But that's what this would really be about. So I guess I'm over here now. Find the force, the total force on the 3 kilograms, which is the one up at the top there. So it's the x-axis, that's the y-axis. That 3 kilograms is located up here somewhere. The 5 kilogram force creates a force, or the 5 kilogram object creates a force that pulls in more or less that direction. I'll call that F1 because that seemed like as good a name as any. And the other one, the 4 kilograms, is pulling right straight down with a force that I'll call F2. If you don't like subscripts, you could call them A and B, I suppose. Gravitational forces are always attractive. You don't have to get into this opposites attract, likes repel thing. With gravity, the force always points right straight at the other object. So kind of like before, well, actually it's going to be a lot like before, except there'll be both I and J components this time. But find each individual force's magnitude first of all. Once I've got those, stick the direction on. Force number 1, magnitude. Newton's inverse square law for gravity was something I covered in physics 131, but I'm pretty sure I included it on the formula sheet for this course as well. It's the gravitation constant, 6.67 times 10 to the negative 11. That's capital G, times the product of the masses, 3 kilograms, 5 kilograms, over the distance between them squared, 0.5 of a meter. So G M1 M2 over R squared is the equation for gravity that corresponds to the Coulomb's law constant times Q1, Q2 over R squared. Very similar kind of thing. And because there isn't very much mass, it's not a very big force at all. 4 times 10 to the negative 9th of a Newton. Same sort of thing for F2. One mass is 3 kilograms, the other mass is 4 kilograms. The separation between them, 20 plus 20, 40 centimeters, 0.4 of a meter. Five times 10 to the negative 9th of a Newton. Now, this is a fairly popular place to make a pretty serious mistake. People get to this point, and then they say, okay, those are the two individual forces. The superposition principle says to add them. 4 plus 5, 9 times 10 to the negative 9th of a Newton. Forces are vectors. You've just treated them, well, not you, somebody else, obviously. Somebody, whoever it is I'm talking about, has just treated them as if they are scalars, okay? You have to express these in terms of their components before you add them together. So, the first one, 4 times 10 to the negative 9. That's the one that points in that direction. It's given in the question that this is 23.58 degrees. Actually, there's enough other information there to figure it out, but I just threw that in as given information to shorten it a little bit. So F1, the vector, I think I'll stick the 10 to the negative 9th out front just because I'm lazy and I don't feel like writing it twice. So gotta adjust my camera. I've got 4 times 10 to the negative 9 on this hypotenuse. That hypotenuse times the cosine of the angle gives me the x component, which points to the left, so minus I for the direction. Hypotenuse times sine gives me the y component, which points down, so negative j for that. And that's negative 3.67 I minus 1.60 j times 10 to the negative 9th of a Newton. I'm almost done. There's only another couple of lines to write. So that's force 1. Force 2 is the easy one because it points right straight down like that. And 10 to the negative 9th. So F1, the vector, is this. F2, the vector, is that. Superpose them. F1 plus F2. The vector sum. Negative 3.67I minus 6.60. I left the J out of this one, didn't I? I'll slip it in there. 6.60J. And that's the answer. That is the resultant force on that mass up at the top due to the combined effect of the other two masses. See you Friday.